Okay, this is going to be a recording regarding a couple of problems that are on the exam, number 3 for chapters 9 through 12. And I wanted to go over it to sort of give you an idea as to how you might approach these. And obviously the numbers are going to be different no matter what you do. But we're going to focus in on here on problem 10.16. And that's a solid disk of radius 8.6 cm and a mass of 1.35 kilograms, which is rolling at a speed of 3.4 meters per second, begins rolling without stopping up a 10-degree slope. Now, the question here is how long will it take for the disk to come to a stop? And I wanted to give you an idea as to what it would take in order to be able to solve this particular problem. Well, let's take a quick look here at what it is, what the situation is. You've got this solid disk that is starting down here, but is going up this particular 10% slope. So, what are the forces that are going to be involved here when it stops? Well, let's take a look here. We're obviously going to have gravity that is going to be pulling straight down on it. Problem is that gravity, of course, is going to have components. It's going to have a component going this way and this way. And we're going to be looking at the motion in terms of this. We're going to call this X and we're going to call this Y. So you're going to have gravity that's going to be basically pulling it in this direction. What force is it that you're going to have going in this direction? Well, as it turns out, the force you're going to be having going in that direction is going to be torque. You basically have this rotating, or you've got rotational motion going up in this direction. Now, you've got torque, and that is going to be, of course, RF sine of the angle between them, which here you've got the force going this way, you've got the radius going this way, so essentially the sine of theta here ends up 1. Another way, of course, to write torque, which again is rolling this way, which means the force is going this way. It's going to be the moment of inertia times the angular acceleration. Now, what is R in this case? R, we know, is going to be 8.6, but for right now, I'm just going to leave this as just R. What is the force going to be in this particular direction? Well, we know that the force in this particular case is going to be mass times gravity. It's going to be pulling down in this direction. Now, obviously, it's not going to be just gravity pulling down because it's broken up into components. And if you go through the mathematics here, you find out that the 10 degrees here is going to be the same thing as 10-degree angle here. If you take the sine of that particular angle, that's going to be the component that's going to be pulling it down. Now, what is this going to be equal to? It's going to be equal to the moment of inertia times the angular acceleration. Now, the moment of inertia in this case, if you look it up for a disk, for just a disk, you might think, oh, okay, it's going to be 1/2 mr squared. That is going to be at the center here. What we're going to be looking for is the torque. And if you look at the edge of a cylinder, this is going to be your moment of inertia. So you're going to have 3/2 mr squared. And then you've got the angular acceleration. What is the angular acceleration? Well, again, we have no real idea what the angular acceleration is. All we have here is a speed, essentially, of velocity. Well, remember that this is the same thing as A over R. And remember that A is going to be the change in velocity over R. And that is going to be with respect to time. Now, in this particular case, the time here is going to be going from basically from here up to this particular point. So that change in time, I'm just going to write as t. And the change in velocity is going to be from 3.4 down to 0 because it goes to stop. So I'm going to represent it with v is equal to rt. Not v is equal to rt, but v over rt. And so there we have it. Now, that cancels with this. And so what does that leave us with? It leaves us with r mg sine of 10 degrees is equal to 3/2 m r v and all over t. So now let's take this, and you'll notice that the r's here will end up canceling on both sides. The mass is going to end up canceling on both sides. So what do we end up with? We end up with g sine, in this case, of 10 degrees. It could be, whatever this slope happens to be. And that's going to be 3v over 2t. And since the question is, how long does it take for the disk to stop? I'm going to take this, move it over here. We're going to say that if we solve for t, t is going to end up being, let's see, t goes over here. This goes over here, so that leaves us with 3v divided by 2g times the sine of 10 degrees. And that's where all of that comes from. So that's the explanation here, is that basically we have gravity that's working this way, and we also have the torque that's moving up this way. And so the torque and the force of gravity here, these are going to be offsetting each other. So this torque should be equal to, basically the force going this way is going to be the same as the force that cancels out by going this way. So that's where that comes from. Now, we have another problem here. Do that. And let me see if I can do it real quick. Not this one. Very well be this one. There we go. This is the one I'm just going to solve. We have a solid uniform sphere of mass 5 kilograms and radius of 0.1 meters, and it rolls down an inclined plane without slipping. If the sphere center of mass moves through a vertical distance of 1.8, what is the rotational work done on the sphere with a static friction force? Okay, this question is somewhat tricky, and here's why. Essentially, you have the sphere, and this is going to look a little bit close to what the problem just finished working was, but we've got the sphere that's right here, and it's rolling down this direction, and it's rolling down an inclined plane without slipping. And that's the key part right here, without slipping. It doesn't really matter how the sphere's center of mass or how far that ends up moving. what we're concerned here is the work done by the static friction force. Now remember, work is equal to force times distance. This point on the sphere, this contact, is never the same point as it rolls along. So you never have a case in which the ball or the sphere is just scooting along. Now, if it were scooting along, we would actually have a force that's being applied by the static friction. If we knew what the mass was, we could figure out gravity, things of that sort and whatnot. But it's never the same point here. The point I'm trying to get at is that while this ball does move a certain distance down, it's the static friction force, since it is not slipping, is never really actually being applied to this particular sphere. And because of that, the force is equal to 0 newtons. Then you multiply that by the distance or whatever else, and that's why the work in this particular case is considered to be 0, because the static friction force never actually gets applied. This thing is rolling down smoothly. There's actually no choice, there's no chance for the friction force to actually be applied. So I hope going through these two problems helps to explain why the answers are the way they are.